Welcome back, everyone. Now we're going to go ahead and keep working with some vectors, but we're going to take a more algebraic approach to them. And to start, I'm going to start by drawing a vector PQ where P is at 0, 0 and Q is at 6, 8. Okay? Now, we've talked about this before. I could break up this vector into a horizontal component and then a vertical component, horizontal, vertical, and we could rewrite this vector differently. So instead of writing vector PQ all the time, one of the notations that we commonly use is this little bracket notation, which is universally accepted as meaning that we have a vector, and the components of that vector would be horizontal and vertical if it was 2 dimensions. 3 dimensions, you just have another component. But in this case, the vector PQ, we'd have to go right 6 units and then up 8 units. So we'd say that vector PQ has a horizontal component of 6 and a vertical component of 8. Okay? Now, in general, if P is at x1, y1, and Q is at x2, y2, we would say that vector PQ, you could write it in vertical and horizontal components by simply subtracting. So for instance, let's say P was not at 0, 0, but somewhere else, we would take final, which is x2, minus initial x, which is x1, and then do the same with y. So final y minus initial y. Always has to be in that order. Okay, so this would always give you the horizontal and the vertical components. Okay. Now, in addition, here's another helpful tip or definition. Let's say V, a vector V, has components A, comma B. So the horizontal is A and the vertical is B. That means that I have a vector that has a horizontal of A distance and a vertical distance of B. So now if I wanted you to find the magnitude of V, or the length of vector V, one way to do it would be to say, well, I could just do a right triangle and do Pythagorean theorem, so that this length over here, which is the magnitude of V, that, whoop, sorry, I'm mixing in my other notation for Calc 3. We're just calling it magnitude V with one absolute value bar. That would be, if I squared it, that's like the c squared in the Pythagorean theorem. We'd say c squared is a squared plus b squared. So if I took the square root, we'd say that the magnitude is just the square root of a squared plus b squared. So there's a nice little shortcut for finding the magnitude or the length of a vector. As long as we know the horizontal and the vertical components, all this means is to take the square of the horizontal component, the square of the vertical component, add them up, take the square root, and there's your length or magnitude. Okay? So here's a quick example. Let's say P is at 3, negative 4, and Q is at negative 1, 2. And the question is, find the magnitude of PQ. Well, one way to do it would be to say that PQ has horizontal component of -1 minus 3 and a vertical component of 2 minus -4. So we get -4 for the horizontal and 6 for the vertical. So then the magnitude of PQ would now just be the square of -4 and 6 added up. Take the square root, so that's going to be root 16 plus 36, which is square root of 52, which is 2 root 13. So the length of the vector from P to Q is 2 root 13. Okay, so that's kind of some basics there. The rest is really just some more algebra stuff that we can do. So let's bring that in, vector algebra. And here are some basic rules. Hey, Jamie.
I had a question about somebody in our class.
Okay.
So I'm in your book and we need to find out this thing. You know who that is?
That guy right
Yeah, the
there?
guy.
I can't make it out.
He sits like,
He's in our class?
yeah, he sits in this row.
Jesus Alcantar?
Yes. Okay. Thank you.
Yep. Okay. Sorry about that. Random student asking me a question. Everything's good now. Okay, so back to vector algebra. Here are some basic rules. So let's say we have two vectors. Let's say v, and let's say that vector v has components v1 and v2. Let's say we have u, and that vector u has components u1 and u2. Okay, now the definition, if I wanted to add vector v with vector u, we talked about how to do that geometrically yesterday, and then how we can find the length, and we draw it on the coordinate plane. The other way to do it would be to say that if I have the horizontal components for each of them, you simply add the two horizontal components together to get a new horizontal component, and then you do the same thing with the vertical components. So you simply take the two horizontals, add them up, the two verticals, add them up, and that creates your new vector, v plus u, which will look like that. And subtracting is really the same. You would just do v1 minus u1 and v2 minus u2. Okay? So that's addition. Multiplication, there's two types. We have something called a scalar multiplication. Which means that we have some number, let's call it k, times a vector. Anything that's not a vector, we're going to call a scalar. That's just like a constant or just a number. Okay, and we know what v is from before, so this just means k times the vector v, which is v1 comma v2. And all we do for scalar multiplication is just distribute the k in. So our new vector would be k v1 and k v2. Now, this is something that we're not going to do too much of, but it's worth mentioning. There's something else called a dot product, which is something that you will deal with a lot in physics because it's related to work, and it's just a different way to combine vectors via multiplication. And here's what the definition looks like. So if I wanted to take v dot u, using the definitions from above, that's v1 comma v2, and we don't say times, we say dot. It's literally a dot. So that's if I take v1 comma v2 and dot it with u1 comma u2, the dot product operation is simply multiplying the horizontal components together, So that's v1 times u1, and then adding that with the other product. So we take v2 times u2, and we add those two numbers up, and now we get a scalar. A scalar meaning we get some number here. So that's actually one of the important differentiations between the two types of multiplication. When you take a scalar, just a constant times a vector, you just get another vector that's either larger or smaller, but really the same direction. When you take the dot product of two vectors together, you're actually going to get just a numerical answer. This is not a vector. Okay? So when you add all these up, you're going to get an answer. All right, so let's do an example that does a whole bunch of algebra with vectors. Let's say I have v equal to the vector 1, 2, u equal to the vector negative 9, 3. And let's say w is 4, negative 7. And let's say we're going to do a whole bunch of stuff. So part A, let's say I wanted to find v plus u. Part B, let's say I wanted to find the magnitude of v minus the magnitude of 3w. And for C, let's say I wanted to take 2v minus 3u. And for D, let's say I wanted to take v and then dot it with w. Okay. So these are all very easy computations to do as long as you remember the rules. So for v plus u, that means we're going to take the components of v, the components of u, and just add them up. So 1 plus negative 9 gives me negative 8. 2 plus 3 gives me 5. There's my answer. So when I combine these two vectors by addition, I get a new vector with a horizontal component of negative 8 and a vertical of 5. Okay? B, remember that this notation means length of v, and that this notation means length of 3w. Okay, so the length of v, I know I can just square the horizontal components, so that'd be, and the vertical components, that'd be 1 and 4, add them up, so we're just going to get root 5 there. And now this one, let's write out 3w. So what is 3w? 3w is going to be w but tripled, so 12 and then negative 21. Alright? And now if you add those up, well, square them first. I'll use my calculator here. This means that find the length of this vector over here. So we're going to do square root of 144. That's 12 squared. 21 squared is 441. So we get root 5 minus 585, root of that. Square root of 585, not a perfect square. Looks like I can divide by 9. So then that would be root 5 minus 3 root 65. 65 is just 5 times 13. That doesn't break down anymore. So the best answer would be root 5 minus 3 root 65 if you reduce the radical there. Okay? So important distinction here. When you add two vectors together, you get a new vector. Here you're finding the length of one vector and subtracting the length of another vector, so you're going to get just a numerical answer. This is not a vector here. Here I'm doubling a vector and subtracting another vector that got tripled, so we're going to get a vector for an answer. And from before we talked about this, when you take the dot product of the two vectors, here we're going to get just a number for the answer. All right, so let's do this one, 2v. Well, looking above, if v is 1, 2, when I double it, I get 2, 4. And now I'm going to subtract triple of u. u was negative 9, 3, so that becomes negative 27 and 9. So I'm just tripling negative 9, tripling 3, and then I'm subtracting those. So then I get 2 minus negative 27 is 29, 4 minus 9 is negative 5. So there's that answer. And now v dot w, that just means to take 1 and 2 and then dot it with a vector that has 4 and negative 7 for the components. Remember that just means to take 1 times 4, so take horizontal times horizontal, plus vertical times vertical. So that's going to be 4 minus 14. The answer is going to be negative 10. Okay, so that's dot product, some scalar multiplication and subtraction. Same thing here with finding lengths and magnitudes, and here was just basic addition. Okay, now some other things that are in this section. Let's introduce unit vectors. So let's say we have the xy axis. Along the x-axis, we have a unit vector that's 1 unit long, and we also have a unit long vector in the y direction, which is 1 unit long. If I wrote the green vector in component form, I'd say, well, that the horizontal is just 1 unit long, and the vertical has 0 because we're not going up or down at all. And now if I did the same with the vertical vector here, from origin, I'm not moving left or right at all, so horizontal component is 0. But then I am going up 1 unit, so that'd be the vertical component. Okay? These have special names, and we call them I. So the unit vector in the horizontal direction is defined to be 1, 0, and a unit vector that's in the y direction is defined to be 0, 1. Okay, so what this allows us to do, sometimes you'll see vectors written in a different form. So, for instance, if we have a vector v that has v1 and v2 as the components, we say that if you don't want to write it in component form, you could just say, well, the horizontal component is v1, and we have the horizontal unit vector as 1, 0, so we can write it as v1i plus, and then the vertical component for v would be v2, so it'd be like saying we have v2 of these little unit vectors. So that'd be v2j. Okay, and if you don't see why this works, a quick verification: v1, the unit vector I is 1, 0. v2, the unit vector j is 0, 1. If you actually perform the scalar multiplication, you get v1, 0 plus v2, 0, or 0, v2. And then now when you add these two vectors together, v1 plus 0 is v1, and 0 plus v2 is v2. So, I mean, you get the same vector again. Okay, so it's pretty straightforward. It's kind of like when we had logs and stuff like that. You had different ways of writing the same thing, and it meant, that the same exact equation. With vectors, so if I have negative 7, 11 as the vector in component form, If I wrote it in ij form, that'd simply just be negative 7I plus 11j. So this is what we call ij form. Another quick example, going the other direction. If we have the vector negative 4I plus 6j, if I wrote it in component form, it would just say that the horizontal component is negative 4 and the vertical component is 6. Okay, so these are pretty straightforward computations. Okay, now we just have two more little problems that are somewhat common in this section. Find a unit vector in the same direction as the vector 9, 40. Okay. So let me draw a picture, and then maybe you'll see what the shortcut's going to be. So we have a vector that has a horizontal component of 9 and then a vertical component of 40. And then this vector, if I drew it, would look something like this then. Okay? So horizontal 9, vertical 40, that's this green vector right here. So this green vector represents the vector 9, 40. Okay? Now, the goal here is to take this vector and to find a vector that's only 1 unit long in the same direction. Okay, so the easiest way to do that is first to figure out how long this vector is. Okay, so currently, the vector 940, if I square 9, you get 81. If I square 40, you get 1600. If I add that up and take the square root, actually I think that's a Pythagorean triple if I'm not mistaken, you get that the length is 41. So that currently this vector here is 41 units long. I mean, and you've seen this picture before, right triangle, 940, 41 units long for the hypotenuse. So the idea here is that we're going to scale this vector down so that it's 1 unit long. So what we can do is say, you know what, let me divide by 41 so that now this becomes 1 unit in length. And if you divide one side of the triangle by 41, everything gets divided by 41. So that now this vector here, this orange one, maybe this orange one is 1 unit long. And now the horizontal component and the vertical component would be 9 over 41 and 40 over 41. Okay? So the idea is, if you want to find a unit vector in the same direction as any given vector, first, you find the length, and then second, you just take each component, 9 and 40, and you divide each component, divide each component by the length. So pretty easy to do. Okay? Last problem. Find a unit vector that makes a 150-degree angle with respect to the positive x-axis. So here's positive x. 150 looks something like that. We want to know what this x value has to be and what this y value has to be. So what's this horizontal and vertical component? so that this vector is 1 unit long. Hopefully you guys already see this. This is just the unit circle, 150 degrees. We know the coordinates here. The horizontal component, which really represents the x-coordinate, would be negative root 3 over 2, and the vertical component would have to be 1/2. So we're done. Okay. Last thing I want to mention, anytime they ask you to find a unit vector, if you want to be real sure that what you have is correct, when you find the length of your answer, it should be 1. So, I mean, if you quickly check, if I square root 3 and I square 2, that's 4. And if I add that with 1 squared and 2 squared, we get 4/4, right? And if I square root that, that certainly is 1. And if you do that up here with this previous one, it's the same idea. So if you do 9 over 41 squared plus 40 over 41 squared and square root that, that's also going to give you 1. Okay, so these vectors here are just shorter versions of the same vectors in the same direction, just 1 unit long. Okay? Alright, so that wraps up the first half of the unit. The last part of the unit we will start later on. Farewell.